Hey everybody, so in this video I want to give you an in-depth tutorial on one of the most fundamental, but what I think is one of the most misunderstood aspects when it comes to AI and LLM models specifically overall, and that is with regards towards memory. And then specifically understanding memory and AI agents is what I want to dive into here. Starting off as an introduction, artificial intelligence agents are transforming how we interact with technology. However, one of the fundamental challenges in creating truly intelligent agents is giving them the ability to remember and learn from past interactions. Without memory, AI agents are stateless. Each conversation is isolated with no knowledge of previous exchanges or accumulated experience. And this is very important. I'm going to dive deeper into this in just a second. This tutorial explains how memory systems work in AI agents, drawing parallels from human cognition to create more natural, personalized, and effective AI assistants. Overall, this is what I think is, to me, the most misunderstood aspect of this overall. And then, so I want to highlight and talk about kind of how your typical LLM model works out of the box when it comes to memory overall. So, out of the box, your typical LLM model doesn't have any memory overall in any way that you would typically think of it, right? It has no long-term memory, which means that any sort of context between conversations is just going to drop off. Like once that conversation ends, boom, that's the end of the conversation, right? And the end of its memory of anything associated with that conversation. And that's the kind of big point and aspect within that, right? Because the model does have and will have a memory during that conversation, and that like during that conversation window. And I think that aspect of it is what tends to throw people off, because that memory is both limited and also operates counter to how human memory works on that level and within those aspects, right? And then what I mean by that very specifically is that so that context window is essentially the memory that the model has during a conversation. And let's say that the model has a context window. General context windows now are getting larger and larger, right? Between 250,000 to 2 million tokens is generally that window. And then once that fills up, the model just has to delete something from its essential memory within that. Also, too, within that context window, the more that context window fills up, the more it actually degrades model performance. So, like, model performance is actually at like 100% with a completely empty context window, and then the more that you fill it up, the more the model degrades down to like 1%, the higher that context window fills. And that's important to understand within this overall. And that leads us to like, why exactly do AI agents need memory? And so large language models are inherently stateless. That's the term to understand within this. Each API call is independent, creating several critical limitations. This leads to no context retention, meaning that the model cannot remember what was discussed in previous conversations, as I just laid out. Repetitive interactions. This leads to repetitive interactions where users must re-explain context and preferences repeatedly because the model can't remember them. This leads to very limited personalization overall, which is a big aspect when it comes to agents. The agent cannot adapt to individual user needs and communication styles, as well as inefficient problem solving. So you can't build on previous solutions or learn from previous mistakes. Memory systems bridge this gap, enabling AI agents to maintain context, learn user preferences, and provide increasingly personalized assistance over time. And then what I want to dive into, and what we're going to dive deeper into in the rest of this, is the different types, modalities, and kind of frameworks of memory that are available, right? And it's important to understand that there is a multitude of frameworks available for memory, how it works, etc., because fundamentally there are aspects of memory that we don't fully understand, is the bottom line within this, right? Like, I cannot clearly and distinctly tell you what the difference is 100% fully between human memory and, let's say, RAM on a computer, right? Um, I know 1,000,000% that those are two very different concepts, but like, what is the 100% internal workings of the human memory? That's the aspect of it that I can't go deep and dive into. I can go into 100% of the aspects of how RAM works overall, which is um, 100% deterministic, right? And then so most of the memory approaches that we're going to go into within this are deterministic memory approaches, whereas in my experience, my research, and what I focus on within this, my assumption is that there's a probabilistic aspect to human memory overall, and I think that is lacking in a lot of these frameworks and models. And then so I do want to highlight that diving into this. But first of all, I'm just going to go with the 100% conventional. This is what you would learn from every other video, lecture, etc. that you would go into within this, right? Diving into types of memory and AI agents. So, drawing inspiration from human cognitive psychology, AI agent memory can be categorized into several types, each serving distinct purposes. The first type is short-term memory or working memory. And the purpose of short-term memory is to maintain immediate conversation context and recent exchanges. Characteristics of short-term memory is that it's very limited capacity, right? Like, it's the last 5 to 20 messages. It allows for fast index access with no indexing required, operates as a sliding window of recent interactions, and automatically forgets older messages as new ones arrive. An example of this would be remembering that the user just asked about Python debugging in the previous message, allowing the agent to provide follow-up information without requiring the user to repeat the context within that. Short-term memory is generally like you generally like just put it within like your Python or your JSON file, and you just build out like a small table within and wrap it around the model where you just have it store these things. Overall, you don't generally put a lot of limits within it. Like you want it to store not full like sentences, etc., things like that. Generally, is the limitations that you put around it, and then it's, as it says here, 5 to 20 messages. That's very typical within a short-term memory process, right? But then within that, you generally want on top of that. So, and all of these work together, right? It's not like you just pick one of these. Generally speaking, you pick a multitude of these, or you pick a framework, a sub-framework within all of these, right? So you have a framework for short-term memory, for long-term memory, episodic memory, procedural memory, which we'll dive into, right? And then so diving into long-term memory or semantic memory, the purpose of long-term memory is to store persistent facts, preferences, and important information about the user. Characteristics of long-term memory include unlimited capacity, which is database-backed, requires retrieval mechanisms, so you need a vector similarity search or something similar. It persists across multiple conversation sessions, and it's organized using semantic embeddings for efficient retrieval. So an example would be storing that the user prefers Python for backend development, works on machine learning projects, and has a dog named Max. Information that can be retrieved weeks or months later. So the bottom line to understand with a long-term memory is that the difference between long-term memory and short-term memory is that you're introducing databases instead of just flat-out tables to the equation overall within this, right? And that's kind of the bottom line of how that works out overall within this general discussion is that, so with long-term memory, you're introducing two database tables. Typically, generally speaking, you're introducing like a SQL database generally. So just general SQL or like a Kubernetes or anything like that, and you also need a vector database. So essentially, your typical SQL database structure is the way that you would typically store and retrieve facts for humans, and then you also need that same type of structure for the AI model itself, right? The AI model needs to have that information vectorized, and then so within that, it's going to need some sort of like ability to vectorize and have access to a vectorized database that is in addition to your SQL database. So within this, you're essentially spinning up two databases, and that's kind of the concept that I think a lot of people struggle with within this. Then you have episodic memory, and episodic memory is different from long-term memory, right? So episodic memory, the purpose of this is that it records specific events and experiences with temporal context. With temporal context is the important aspect to understand and what differentiates episodic memory from long-term memory. And then so the characteristics of episodic memory are that it's time-stamped and contextually rich, captures the narrative of past interactions, and enables time-based queries and temporal reasoning. Again, that concept of temporal reasoning. So an example would be on November 10th, the user asked about debugging async functions in Python. On November 12th, they requested help optimizing database queries. And then so diving into this aspect of this episodic memory as opposed to long-term semantic memory, the key concepts, as I've mentioned kind of repeatedly within this, are temporal context. And then so if you're not aware, just fully within that term, it's referring to like a sort of like a time-based or time-stamped sequence within this. You're introducing time plus memory to the equation, right? And then so that would be that like the existence and the knowledge that there's days of the week, days of the month, a calendar exists, etc., right? And then your minutes, hours, etc., and you're laying that additional layer on top of the event itself, which is important, right? That's the like kind of that episodic loop that you want to create within the memory structure of the memory itself within that. And then so generally speaking, you would for episodic memory and then breaking these down, you do it via tables, right? And so it's the exact same concept of like SQL and vector-based tables that you have here for your long-term memory, but for episodic memory, you have an additional table. So like within this, you're getting into, you can see the complexity start to explode within this, right? What you would think is just a very simple problem within this, like, oh, my model needs more memory or needs memory period, becomes a very extensive and a drawn out problem the more that you put in this, right? You're putting a bunch of scaffolding around the model is what ends up happening. Like you're putting a bunch of database scaffolding very specifically, and that's where people struggle within it overall. And then so that leads us to the final concept of memory overall within this, which is a procedural memory. And then so the purpose of procedural memory is that procedural memory stores learned patterns, workflows, and user-specific processes. The characteristics of procedural memory are that it captures habitual behaviors and preferences, adapts to users' communication and work styles, and it's continuously refined through repeated interactions. An example would be that learning that the user always prefers detailed code examples with comments, or that they typically work on projects in a test-driven development style. The number one way to handle and to implement procedural memory in the status quo is like RAG tuning, right? Like so generally speaking, when you hear about like RAG tuning, and very specifically when it's tying to memory, very specifically what they're giving the model within that is some sort of like access and build out for procedural memory. And then the other aspect within that would be fine tuning as well. So like RAG tuning and fine tuning are very specifically what the main functions and the main aspects of procedural memory are within this instance. So the previous aspects, like so with short-term, long-term, and episodic memory, all of these are designed around creating databases, right? Where essentially you're creating databases that the model then essentially is dumping data within and then storing data within. Whereas procedural memory, it's the opposite equation, right? Where these databases are already built out, and the model is accessing and the information that's stored within the procedural memory database. Or like the RAG tuning database in this instance, or what it's being fine-tuned on overall. Diving into the technical implementation overview. So implementing memory and AI agents involves several key technical components working together. The core components are one, embedding models. So embedding models convert text into high-dimensional vector representations that capture semantic meaning. These numerical vectors enable similarity comparisons between different pieces of text. Common models would be sentence transformers, OpenAI embeddings, or Cohere embeddings. Typical dimensions would be between 384 and 1536 dimensions, and then that's all based off of essentially like your typical scaling, and you need to split out your dimensions and into different layers, etc. So like the same kind of like principles that fall under and are typically associated with like RAM, hard drives, etc., fall under dimensions when you're talking about dimensional embeddings. And then the purpose of embedding models is to enable semantic search and similarity-based retrievals. And then so it's important to understand that within these models, you have essentially encoders and decoders, right? And then so the encoder's job is to encode embeddings, and then the decoder's job is to decode the embeddings that the encoder has produced. And then so within that, very typically, like you can have a very small model that is the embedding model itself. And then so specifically, and as we're talking about AI agents overall, that's generally the approach that is taken overall within this, right? Is that your embedding agent is generally like a very small model and small agent that you have within this. And within that, and then secondarily, you have vector databases. So vector databases store embeddings and enable efficient similarity search at scale. They use specialized indexing structures like hierarchical navigable small world for fast approximate near neighbor search, or KNN search. So popular options of this would be like ChromaDB, Pinecone, Weaviate, Milvus, or Quadrant. And then key operations would be like insert, query by similarity, update, and delete. And the scalability of them is that they can handle millions to billions of vectors efficiently. So generally speaking, again, like you have to have this aspect within your memory models in order for them to work overall within this. Essentially, like a vector database is just a database that is machine readable and machine learnable. Your SQL database itself isn't going to be machine learnable and machine readable off the bat and out of the gate, and then so you need to vectorize it. And then so generally speaking, your vector database goes hand in hand with your SQL database. And then within that, and directly tied to that, you need retrieval mechanisms, right? And then so the retrieval system determines which memories are most relevant to the current context and should be included in the agent's prompt. So within that, you have semantic similarity, so finding memories with similar embedding vectors, temporal filters, which prioritize recent or time-relevant memories, hybrid search, which combines keyword matching with semantic similarity, and then relevance scoring, so ranking memories by importance and applicability. This is the big aspect of, like I kind of hinted around this earlier, right, where the big problem when it comes to memory overall within this, like the big gap within it that I can't fully explain to anyone overall, right, myself included, is how exactly human memory works 100% within this equation. And then so like these concepts combined, semantic similarity, temporal filters, hybrid search, and relevant scoring, are really kind of like the computer science version of how it's assumed that human memory works overall within this equation. And then so that's essentially how these retrieval mechanisms are structured, and how and why they're structured the way that they are. And then so the next one that you have within this is memory consolidation. So within memory consolidation, like human memory, AI agents benefit from consolidation, the process of transferring important information from short-term to long-term storage, which includes extracting key facts from conversations, identifying patterns and recurring themes, and then filtering noise and retaining meaningful information, and updating or merging conflicting information. And bottom line within memory consolidation, like this is I think a underlooked aspect that is under researched and underlooked when it comes to these models overall, right? So as I mentioned within all of this and multiple a multitude of times, all of this is essentially just different databases, right? It's different, a plethora and a multitude of SQL databases and vector databases, and that's it, right? SQL plus vector databases, and then you need a lot of them. Like they scale like kind of like quadratically, right? And then within that, and because of that, like you really need to focus on the memory consolidation aspects. Like you don't want to just throw. It seems easy up front. We're just going to throw everything into the database, right? But then when you have 1,000+ users, and then you're just throwing everything into the database, and you're throwing everything in there, that fills up very quickly. Like you run into like some massive memory problems, right? So you need to confront that problem very quickly of memory consolidation, and then that memory consolidation just essentially breaks down to how and why do you prioritize certain memories or certain facts over other ones, and then remove those and filter those out. And then that's like kind of another aspect of human-based memory that I can't tell you 100% how it works overall. And then so this is, to me, like probably we get like more and more experimental within our knowledge of these things the further that it goes down, right? And so this is the last one and the most experimental one with regards towards how exactly memory consolidation works overall within the human brain. Overall, it's hard for me to I don't know. So everything with regards towards memory consolidation at this point with the models is just really like specific algorithm based is how that runs. And then so next thing we're going to look at here is a memory architecture comparison table. So the following table compares the characteristics of different memory types, and then so you just have short-term, long-term, episodic, and procedural, just simple the different characteristics between the different ones and it's all like a trade-off. Think of this as the same exact trade-offs that you have when it comes towards computers and computer memory overall, right? Like so. Within like computer memory, you have your processor, and then directly next to the processor, you've got like the system bus, right, which is your very first memory, and then it's like from the system bus, then you have your RAM, which is further away from the processor, and then further away from the processor from that is the hard drive, and then so the each one of those is getting further and further away from the processor, but each one of those becomes bigger and bigger with regards towards its actual storage capacity, right? And that's kind of the bottom line breakdown within this and within all of that and how it works within computers, right? Sure, you would want to put like all of your memory in the system bus, give it like a 5 terabyte system bus, and you'd be good to go, right? But it's literally infeasible to do that. Like you can't have a 5 terabyte system bus, but you could have a 5 terabyte hard drive. You're just going down deeper within the chain of a memory within that, right? And then so you have trade-offs within that. Like your hard drive's not going to be nearly as performant as your system bus, but you can get it up, as we've just illustrated here, much higher in regards towards scaling, right? And so it's always just dealing with those trade-offs, and then within AI, it's no different. So best practices for AI agent memory. Implementing effective memory systems requires careful consideration of privacy, performance, and user experience. Privacy and security. Never store sensitive information. Passwords, API keys, social security numbers, financial data, or health records should never be stored in memory. Implement user consent. Users should explicitly opt in to memory features and understand what information is being stored. Provide deletion mechanisms. Users must have easy access to view and delete their stored memories. Encrypt stored data. All memory data should be encrypted in both in transit and at rest. Implement access controls. Ensure strict user isolation in multi-tenant systems. With regards towards memory management, set memory limits. Prevent unbounded growth with configurable size limits. Use importance scoring, so prioritize retention of high-value information. Consolidate similar memories, so reduce redundancy by merging related information. Implement forgetting, like remove stale or outdated information periodically. Handle conflicts, so develop strategies for managing contradictory information. With regards towards retrieval optimization, you have several different options like hybrid search, relevance scoring, recency bias, cache, frequency, access memories, and limit retrieval count. I'll let you dive deeper into these aspects overall. Essentially, everything that we're going through here with regards towards the best practices is just breaks downs and best practices with regards towards all of these concepts up here, right? So it's just distilling it down into a deeper level within that. And then same thing with real world applications overall of where and how you would want to utilize AI agents. So just diving down to the conclusion here for this document, memory is fundamental to creating AI agents that feel truly intelligent and helpful. By implementing robust memory systems inspired by human cognition, we can build agents that provide increasingly personalized assistance over time, reduce user friction by eliminating repetitive context setting, build genuine rapport through continuous learning, as well as deliver more valuable insights by connecting patterns across interactions. As the technology continues to evolve, memory systems will become more sophisticated, privacy preserving, and seamlessly integrated. The future of AI agents lies not just in their ability to process information, but in their capacity to remember, learn, and grow alongside the humans that they serve. By thoughtfully implementing memory with attention to privacy, performance, and user experience, we can create AI agents that truly enhance human capability and feel less like tools and more like trusted assistants. With all of that being said, and with all of this overall, the next step that I always like to do within this is, so I've talked about this in regards towards the concept overall. What does this actually look like when you break it down into the code and actually like want to implement an agentic system with memory around it, right? So that's exactly what I'm going to showcase here for you in this AI agent memory tutorial. In this, for prerequisites, you're going to need some basic Python knowledge. Familiarity with AI and LLMs is helpful, but not 100% required. And then in this notebook, there's no API key required because we're not going to utilize real LLMs, but I'm going to give you the option to utilize real LLMs if you want to. And then so first setup is, first we need to run through set up an installation, which is essentially just installing some required packages. And then within this, we're including a mock LLM system so that you can explore immediately. If you want to, you can also use OpenAI and provide an OpenAI key, which will provide you have the ability to provide and update here if you want. And then second thing here, then we go into is understanding AI agent memory. So why do AI agents need memory? Again, all of the concepts that we dove deeper into within the doc there are available here for you. And then here's the actual implementation of it, right? So here's what we were talking about before. Now, how do you actually implement short-term memory? This is the simplest form of memory is keeping track of recent conversations. And then as you can see here, we have our simple cell here for essentially defining and initializing short-term memory. So within that, we create our arguments, which we have our max number of messages, and then what messages and what data we want to store within those messages. And then we within this, we're testing it, right? And then so within this, we have the short-term memory contents. So hello, my name is Alex. Hi, Alex. Nice to meet you. I'm working on a Python project. That's great. What kind of Python project? And then so we can see within this, it's because there's only 4 messages. It's storing all 4 messages within that, which is exactly what we would want. And then from there, we can do a long-term memory, right? So long-term semantic memory. So for long-term memory, we need a way to convert text to embeddings. Again, that whole process. So we need to store it like as a SQL, but then we also need to store it as a vector representation, as a vector database as well. So we need those 2 databases. And then because it's 2 databases and we need a way to both get the data into those databases as well as retrieve it from them. So we need a retrieval mechanism that we need to build out within that. And the retrieval mechanism needs rules in order to operate. And then so as you can see here, that becomes a lot more complicated, right? And then so that's what we have here. In this instance, I'm building out and then just adding a simple vector store and vector database and creating my databases within the code here, right? And then so this is the simplest way that you can do it with no external databases. It's but this would fill up very quickly within your code, but it gives you the option to do that, right? And so you have long-term memory, and then so in this instance, we added 5 memories to our long-term memory storage. And then the next step is to play around with this. I'm utilizing a mock LLM system within this just to get it up and running. But you can utilize anything that you can utilize real AI models within this, and you have access to just a simple update of the code in order to utilize a real model. And then from there, we want to build a complete memory-enabled agent. So we want the whole entire thing, and then this is where you would put your OpenAI key if you want to actually like have it actually build out and be a real agent. That's all you would have to do. And then we want to test it, right? So we want to test exactly how it works. So in this instance, we're having conversations and then creating memory. And then in these instances where like these are what the memory storage looks like, right? So these are your when it's writing to the database tables, these are like the tables that get written, right? So user's name is Alex and prefers Python for backend development. User's working on a machine learning project about image classification. User's favorite machine learning framework is PyTorch. User asked for help with debugging async functions last week. User's interested in learning about transformer architectures, and then you just do that. And then it's the same exact process for long-term and short-term memory, although what you can see, so long-term memory is structured very specifically for a database table, whereas, again, short-term memory is generally, it's being written very specifically to like the JSON very typically. And then so you're just, no actual table required, right? And then within that, you need to consolidate all of that. So you need to consolidate that short term, those no tables, the SQL tables, and the vector tables, and then all of that. And then if you want some sort of forgetting mechanism within that, you need to build all of that out as well. And then here's just a bunch of exercises, and then further reading and cleanup that you can do, and further exploration that you can do on this topic overall. If this topic interests you and you want to dive deeper into these things, this is a introduction into AI agent memory overall. And if you like this type of content overall, please like and subscribe. Thank you very much.